Today we're going to learn the lesson on 8.1 and 8.2, and it even has a little bit of 8.3 in it for our Algebra 2 book, and it's on exponential growth and decay. So first, let's talk about what the exponential growth and decay function looks like. The equation is y equals a times b to the x power. That's any exponential function, and it could be a growth or a decay. First, if it's a growth, if our a value is positive, but our b value is greater than 1. So the b value is what we call our base. So if our base is numbers like 2, 3, 5 halves, any number that is bigger than 1, it's going to be a growth function. And if you saw what a growth function looks like, it would be obvious that it's a growth function. Similarly, if it's a decay function, your a is still positive, but your b value is between 0 and 1. So in a decay example, your base would be numbers like a 1/2, or a 1/3, or a 3/4. So a fraction or decimal between 0 and 1. And again, if you saw the graph of a decay function, it would be obvious. For example, let's look at number 1. Just off the top of your head, if you saw this function, you probably would think it is a growth, and you are correct. That is a growth function. But if you look at the equation, the y equals 1/2 times 3 to the x power, the base is the number 3, and as we know, 3 is greater than 1, and that's the algebraic reason why this is a growth function. When you look at number 2, this time you can see from the graph that it is definitely decay. And if you look at the equation, since the base is a 1/2 and 1/2 is less than 1, that's the algebraic reason why this is a decay function. When I want to graph a different type of growth or decay, it might be fun to use some technology. So let me just grab my calculator, if it will help. So I have a new calculator today. Oops, maybe not. Yeah, let me go grab it again. Okay, so if I go to y equals and I type in my function, which I think was 2 to the x power, make sure you use the caret button to get up to the exponent, and let's go ahead and hit graph. Now if you have a strange window, you'll want to hit zoom 6 to get back to the standard window. Just off the top of your head, looking at that graph, you should be able to tell that that is a growth function. Now, the other thing it's going to ask us for is to fill in a table. Well, you could do this by hand, using your brain, or you could just make your calculator do this for you. So go ahead to your table, and you're going to see that it's a whole bunch of values, and you just want to pick the values that they actually wanted for your table. So transfer these ordered pairs over to your table on the paper. So when I use a -3, that became a 1/8, which is 0.125. A -2 is 0.25. -1 is 0.5. 0 is 1, then 2, and then 4, and then 8. And then of course you want to plot all of these points. Now it typically won't make you plot this many points. We're just trying to see a pattern. And then you'll notice the numbers start to go up really fast once you pass the y-axis. And that's what it means by exponential. Now, you know my graphs always stink, but you're going to go ahead and graph these. Oh, geez. Woo! Okay, pretend. And you might not see it off of your graph on your calculator, but what I want you to realize is that there's what's called a horizontal asymptote on this graph. It's never going to cross the x-axis down here. So first, I want to know what the growth or decay rate is. And that comes off of our base. So the growth or decay rate for this function, we're going to call it a 2. The y-intercept would be where it crosses the y-axis, and we can easily see that crossed at a 1. And the domain would be how far to the left, how far to the right, and hopefully you can tell that this goes forever to the left and forever to the right, so -infinity to infinity. And the range is how low to how high. Now notice, just a minute, notice that the lowest it goes is 0, but it doesn't actually ever get to 0. So we're going to put a parenthesis on the 0, and then it's going to go to infinity. Now, end behavior is a little strange for a growth and decay function. It's a little different from what we saw on our polynomials, but it's still going to start the same way. And end behavior for us always started like this. F of x approaches something as x approaches negative infinity, and f of x approaches something as x approaches positive infinity. And this is asking what happens when you look way to the left and way to the right. So negative infinity would be looking to the left. Do you see that your function is approaching the value of 0? And that's what we put. So we're not going to go down to infinity for our function this time because of the asymptote. Now as you travel up to the right, notice your function goes up forever. So in this case, it will go to infinity. Okay, next, this time our base is a 1/2. So if I was to put this into my calculator into y equals, I could get my table function to give me all these points. So let's see, 1/2 to the negative third power would be an 8. 4, a 2, a 1. There's a little bit of similarity between these two graphs, and we're going to see what it looks like when we graph it in just 1 second. Alright. And again, I'm not going to make you plot this many points all the time. Now if we tried to connect, and remember, my graphs always look cruddy. It's supposed to be a nice continuous curve here. Hopefully you can see that this is definitely a decay. Oh, by the way, this one was a growth. This one's a decay, and his base is a 1/2. The y-intercept, again, is a 1. The domain goes from negative infinity to infinity. But this time the range still is low to high, and it still starts at 0 and goes up forever. Now our end behavior is a little different. It's going to start the same way. F of x approaches something as our x's go to the left, and our function approaches something as our x's go to the right. So when I look at my graph to the left, you should see that your function's going up forever. So this time it's an infinity up here. And as I travel to the right, it looks like my function's approaching the 0. Let's look at some translations of a graph. So first, on your calculator, I want you to graph 2 to the x power. Maybe you already have it there from a problem we did a little bit ago. So if I hit graph, that's what the original looks like. Now on the same graph, so I want to go to y2 this time, I want you to type 2 times 2 to the x power. Whoops. Times 2 to the x power. And when you hit graph, you should see it go, and you should notice a key difference. It seems to have a different y-intercept. Let's see what happens when I put a 5 in front. So go down to y equals y3. So 5 times 2 to the x power. And again, when this graphs, you're going to notice that this time it has a y-intercept a little higher. So let's try the fourth one. Negative 1 in front. And maybe you've already made a prediction what's going to happen, but interesting. And then if we do the same thing, this time with a negative 3 in front. And again, maybe you've already made a prediction what this will look like. There you go. So the question I have now is, with all of those graphs, can you tell me what is true about the effect of the value for a? Now in the general formula, the a is the number in front of the base. So remember at b, c, d, and e, they all changed. And I think we can all agree now that the a value is going to affect our y-intercept. So here when it was a 2, we had a y-intercept at 2. Here when it was a 5, we had a y-intercept at 5, and so on and so on. And if the a value was positive, this graph was up in the upper part of the quadrants 1 and 2. So in this case, because it was a growth, it looked like this. But if the a value was negative, it reflected it over the x-axis and went down to the lower two quadrants. So let's look at this example. 1/2 times 3 to the x power. I know it's kind of cut off on the screen. Let's see if I can raise this up. Maybe not. All right. So 1/2 times 3 to the x power. I could use my calculator to fill in my chart. I just go to y equals and then plug in all those values. For the sake of time, I'm going to skip over that, but if you'd like to do that, go ahead and pause this presentation. When I fill in my chart, or when I look at my graph, I should be able to tell pretty quickly that this is a growth problem. And the question of the y-intercept. Well, the y-intercept, I remember algebraically, was that a value, so I'm just going to say it's a 1/2. I know that off the top of my head because it's the number in front here. And then the growth and decay rate, I'm going to call a 3, the base. Now, I'm just going to kind of sketch this in right now. I didn't do a very good job. Hopefully yours looks better. Let's talk about domain, because I like to see a picture when I do domain. The domain is still negative infinity to infinity. And if you've noticed, it's always been negative infinity to infinity. Here's a hint. It will always be negative infinity to infinity for growth and decay graphs. The range this time was 0 to infinity. It will not always be this, because sometimes it'll be reflected, and we'll see a case of that a little later. But our end behavior, as f of x approaches something as x approaches negative infinity, I'm going to ask you what happens to the left, and then I'm going to do the same thing for what happens to the right. So as I go to the left, which is negative infinity, my function is approaching 0. As my function goes to the right, as my x's go to the right, excuse me, my function is approaching positive infinity. It's going up. Okay. The next question, I think that says negative x up in the exponent. If you can't read my screen, it says 3 times 4, and then it's in parentheses, to the negative x. Now when you type this into your calculator, you're going to have to make sure that you use parentheses. And I should go and clear out all these other guys. Okay. 3 times 4, and caret. It's always a good habit to use parentheses when there is something more than just one number up at the exponent. Whoops. I did something silly. Let me go look. Oops, I have an extra parenthesis. Delete that. Now graph. And we're going to see a decay function. Now, that kind of goes against what some of you were thinking when you first looked at this. So in our original function, sorry, I paused for a minute, it looked at first like our base was greater than 1, our base was a 4, but did you notice that the exponent was a negative? So technically, this function, remember negative exponents flip your bases, 4 is really going to become a 1/4, and then to the positive x power. So now you can see from the algebra component that this is going to be a decay function. And this is what happens when you graph it. So do the best you can. I'm going to kind of cheat here because I don't have a lot of time. But looks something like that, a lot better. So this is definitely a decay function. The y-intercept is a 3, and it is decaying at a 1, the base is a 1/4. The domain goes from negative infinity to infinity, and the range, still low to high, is 0 to infinity. And the end behavior starts the same way. F of x approaches something as your x's go to the left, and f of x approaches something else as your x's go to the right. So when I look at my function, as your x's go to the left, it seems to be going up to infinity, and as my x's go to the right, to infinity, the function is approaching 0. Okay, the next function is I'm going to kind of cheat, but if you want to go ahead to your calculator and type this in to get your table, that's fine. This is going to be a decay graph, and the y-intercept is going to be at a 5. I can tell that because the base is less than 1, and the number in front is my new y-intercept. So again, I'm going to be a little sloppy here. You're going to be a lot more accurate. It looks something like this. Again, you need to be a lot more accurate. Decay rate, this is a decay of 1/3. The domain goes from negative infinity to infinity, as always, for growth and decay, and the range goes from 0 to infinity. And our end behavior, I'm going to kind of squeeze up here. As my x's go to negative infinity, this function is going to positive infinity. And I always like to write the skeleton out before I answer it. As my x's go to positive infinity, my function is approaching 0. Okay, this next graph, I'm actually going to kind of skip, I hope you don't mind, but it's going to be the same stuff. And if you're curious, this is going to be a growth. It's going to have a y-intercept of 4. It's going to go up like this, and the growth rate, excuse me, is a 2. Domain and range are going to be very similar, and behavior is very similar to our previous problems. So I'm skipping ahead for the sake of time. Now we're going to talk about growth and decay that have now been translated or transformed, either right, left, up, or down, and sometimes reflected. So we're going to use what we know about translations from previous chapters back in this chapter. So first, if I was to graph 3 times 2 to the x minus 1 minus 4, I want you to notice that on your calculator, you have to be very careful with how you type this in. For instance, 3 times 2 caret to get to the exponent. Make sure your exponent is in parentheses because it is more than one thing. So x minus 1, and then close the parenthesis to get out of the exponent, and then subtract 4. Now we're going to compare this to the original 3 times 2 to the x. And it might be a little hard to tell who's who on this graph, but let's see. That's the first one I typed into y equals, and that's the original, the second one I typed in. So you might be able to tell that it's definitely shifted down, and it's definitely shifted to the right. Now maybe you can't tell that off the top of your head, but I can. So let's look at our equation and figure out why we should know that. Look up here by the x. X minus 1. We always talk about shifts or transformations that are near the x as being horizontal shifts. And that's exactly what we have here. So it's shifted h units. And remember, it's always opposite. So x minus 1 is really saying that we shifted this right 1 unit. Now off to the side, the negative 4, that's a vertical shift of k units. So the negative 4 means that we shifted down 4. And we can see that in our graph. Now I'm not going to bother drawing this one because this is going to be really difficult for me to graph, but I'm talking about this graph in particular right here. And it wants to know about my domain. Well, domain on growth and decay is always negative infinity to infinity. But let's talk about the range. It still goes up forever, but look to where it approaches down. And if you're not sure what it does, go ahead and hit the trace button and make sure your cursor is on that lower function. I want you to trace to the left and watch your y values and try to figure out what they're getting close to. They're getting really, really, really close to the number negative 4, which kind of makes sense. If I think about this graph being shifted down 4 units, instead of approaching 0, now he's approaching negative 4. So the range goes from negative 4 all the way up to infinity, and it doesn't actually reach negative 4 ever because it's an asymptote, so that's why we have a parenthesis. So the shift we decided was right 1 and down 4. Okay, let's take this knowledge and move on to the next example. Number 10. Our original graph is 4 to the x, and our new one is 4 to the x with a minus 3 off to the side. Well, subtracting 3 off to the side takes our function and shifts it down 3 units. The domain will still be negative infinity to infinity, because it always is for growth and decay, but our range, because it was shifted down 3, now starts at a negative 3 and goes up forever. Okay, number 11. Our only shift is x minus 1 up in the exponent, so remember that's horizontal and it kind of does opposite, so a minus 1 is really a right 1. The domain is always negative infinity to infinity, And the range, because it wasn't shifted up or down any, is still 0 to infinity. If you don't believe me, you can graph it. Now for number 12, we've got an x plus 1 here and then a minus 2 off to the side. So I think that was shifted left 1 unit, but it was also shifted down 2 units. So for our domain, even though it was shifted left, it's still negative infinity to infinity. And our range, since it was shifted down 2 units, starts at negative 2 and then goes up forever. So the transformations of growth and decay are definitely going to affect the range, but they won't do anything to affect the domain. Okay, this is the second part of the lesson, and probably we broke this up into 2 days, so if you only missed the first day of the lesson, you can probably stop here, but let's keep going. When a real-life quantity increases by a fixed percent, the amount after t years can be modeled by this growth formula. A is the initial amount, R is the percent increase, but it's going to be in decimal form, and then t is the time, typically in years, not always. Now 1 plus R, the stuff inside the parentheses, is called a growth factor. And if we have the same situation, but now we are decreasing the amount over time, we're going to have a decay. So everything is the same, except now it's 1 minus R. That's our called decay factor, of course. So we have a scientist who examines a specimen that starts with 730 bacteria. That's our initial amount. So that's going to be our A value. If the specimen grows by 35% every minute, so this is a case where instead of years, we're talking minutes, write an equation that represents the growth. So I pulled this off of a worksheet where they used A instead of Y, so if it bothers you, you can change this to a Y. But if I use my growth formula, which is Y equals A 1 plus R to the t power, the initial value was 730, and then 1 plus a rate of 35% is 0.35, and then to the t power. Now that's my formula. The next question says, how many minutes will pass before the bacteria reaches 9,000? Now be careful, this is the amount of bacteria that we're going to have after a certain amount of time. We don't know what the t is, so I'm going to use my calculator to figure this out. So grab your calculator. These are your more difficult questions for these. Maybe back in Algebra 1 you did these, but all they wanted you to do was plug in a time and be done. Well, this is a little different. Now you could guess and test and revise, but man, that would take forever. So go to 730 and y equals, parenthesis, 1 plus 0.35, which is 1.35 if you want to simplify that. And then caret to the x power. They don't use t in this mode. Now I'm going to go to my table, which is second graph. And remember, we're trying to figure out where this bacteria gets to 9,000. So we're watching our y values and trying to figure out where they get close to 9,000. It looks like it's in between 8 and 9. So I would be okay if for our purposes you just said between 8 and 9 minutes. But we can get a more exact amount if I look at my graph. Now let's talk about window. My x's represent how much time has gone by. So a normal window for these type of problems usually starts with 0 to 10. We might have to adjust it in the future, but for now we're going to do 0 to 10. And then since I want to know when my y's reach 9,000, I want my y window to kind of come close to 9,000, so a little above it, a little below it. So below it would be like 8,000, and above it would be 10,000. And I don't want to count by ones because that would take forever. So I don't know, let's count by 50s. So now go to the graph. Oops, didn't like something I did. Let me go back. 0 to 10. Oh, I meant to put a 10,000 down here. Try again. Okay, now go to our graph. And you're going to see the curve eventually. There he is. Now if you hit the trace button and you press the right arrow, you can watch a little more closely the y values and see when it gets to 9,000. Now we're 7,000, 8,000, right about there. So roughly 8.4 minutes. So if you wanted a more exact answer, you could use your graph. Let's look at the next example. Later on, we're going to learn algebraic techniques to find the answer. Oops, we should probably fill that in. 8.4 minutes. Okay, we have another problem. We're buying a car for $36,000. That's our initial value of A. This time the value decreases by 14%. Write the model. So y equals, the initial amount is 36,000, and then since it's decreasing, it's 1 minus 14% to the t power. They want us to estimate the value after 3 years. So what you're going to do in your home screen of your calculator is you're going to type in this function, but instead of t, they tell you that they want your t to equal a 3. So I'm actually just going to do this on my own personal calculator. And I get, now this is money, so make sure you round appropriately, 22,898 and then 2 cents when I round appropriately. So now they want us to get our calculator and estimate when the car will have a value of $15,000. So I guess I should have gone ahead and typed this on my screen, but that's okay. Y equals 36,000 1 minus 0.14, and of course you could simplify 1 minus 0.14 to 0.86. Okay, now again you can either use your table or your graph. Since they asked us to use the graph, I'm going to go ahead and do that, but remember we have our window from our last problem. We got to change this. I'm going to keep it 0 to 10 for now, but my y's I want to know when it hits 15,000. So let's go a little below and a little above 15,000. So how about 14,000 and then 16,000. Whoops. Yeah. Cancel. Backspace. Okay, and then again, you count by 50s should be fine. So hit the graph. Eventually it'll show you the curve. And notice this time it's decay. So when I hit the trace button, I'm looking for when it hits as close as possible to 15,000. So I'm getting there. Right around here. So roughly 5.8, let's say. And it's an estimate, so it doesn't have to be exact. So roughly 5.8, and this was t in years. Again, we're going to learn more algebraic techniques later on in this chapter where you can get an exact answer without having to estimate from your graph. And actually, if we got a better window, a smaller window, we could get a really, really close answer. I just don't want to take the time to do that right now. A growth of an antique table's value after 1975 can be represented by this equation. What is the value of the table in 1975? Well, in this problem, they're pretending like the table was born in 1975. So what we're really asking here is what's the initial value of the table? Remember, the A value is the initial value, so that's the $325. And the rate of growth would be, in this case, how far above 100%. We're looking for the R value. So it's 0.03, which we know as 3%. If they asked you for the growth factor, that would have been 1.03, but the rate of growth is just the 3%. Okay, compound interest formula. You deposit $1,000 whoops, in an account that pays 8% annual interest. Find the balance after 1 year with this given frequency. So your bank accounts are usually compounded at a certain rate. This is the formula that we're going to be using to find to find our value. So you deposit $1,000. That is the P, which is the initial principal, they call it in the banking world. R is the annual interest rate, written as a decimal, and N is the number of times that you're going to compound interest. T is the number of years. So $1,000, that's our principal, our initial amount. 8%, which we're going to write as 0.08, that's our rate. 1 year is our time. And then the N, they're going to change 3 times on us. So annually means you collect interest once, so your N is going to be a 1. Quarterly means N equals 4 times a year. And daily means 365 times a year. So in our home screen of our calculator, we're just going to start typing these. So first, for annual, it's 1,000. And then the formula says 1 plus our rate, remember, was 0.08, divided by n, so in this case n is a 1, close parenthesis. Now up in the caret, because it's n times t, you're going to have to use parentheses. So n is still 1, and kind of boring, the t is a 1. So go ahead and type this in the home screen of your calculator, how I have it written there. And you get $1,080. Now we're going to do the same thing, but this time our n's are all going to change to 4s. So you could do this by just pulling up your last entry and modifying it. Oops, caret, don't forget the caret. 4 times 1 right here. So this time I get a little different, $1,082.43. I know that doesn't seem like a big difference to you, but if you were investing a lot of money, that would have made a lot of difference. And then this time daily, we're going to have a slightly different number. A little bit more interest is collected because of how often it's collected. Won't be significantly different, but just a little bit. Oops, that's a times right there. And I get $1,083.28. Okay. Compound interest formula again. This time, they don't tell us how many years. So the question is, what is t? And we want the account to double, and it's going to collect 4.5% interest compounded monthly. So they want the account to double. They don't tell us how much is in the account, but I think it doesn't really matter. The interest rate is 4.5%, so we're going to write that as 0.045. And the n, the number of times you collect interest, is a 12. So it doesn't really matter what you invest, because the ratio of the investment to the final amount of money is always going to be a 2-to-1 ratio. So what I'm going to do is I'm going to say 2 equals, and then 1, and all you have to make sure is that the numbers right here are in a 2-to-1 ratio. So you could have put like a 10 here and a 5 here, or a 100 here and a 50 here. It doesn't matter as long as it's a 2-to-1 ratio. 1 plus, our rate is 0.045, our n is a 12, and then up in the exponent, we got 12 and then t, which we don't know. So now I'm going to go to my calculator, and I'm going to grab y equals, clear out the last problem, and you don't have to type the 2 necessarily, and in fact you don't have to type this first 1, because that's not going to do anything. A 1 is a 1. So I'm just going to type parenthesis 1 plus 0.045 divided by 12, and then close the parenthesis, and then up in the caret, because it's 12t, we're going to have to type 12x, and they want us to use our calculator, so we could either use a chart of the table or the graph. I'm going to use a table this time. Remember, I want my money to double, so I need to see where it's going to go from a 1 to a 2, and I'm watching the y values right there. It happens right after 15 years. So I'm going to say for my answer, because I don't have to be real exact here because it said to estimate, or about, it's going to take about 15 years. Okay. Then this is our formula from 8.3. So if you're in your book trying to take some notes, you can go to section 8.3. This is called the continuous function. The continuous function is a equals p times e to the RT power. We call this PERT for short, kind of a pet name for our function. P is the initial amount that we invest, R is our rate, and T is time. The reason this is a different formula is because this time your interest is compounded continuously. So there's not a set number of times, it's just always compounding interest. So first, number 18, 1,000, sorry for the bell, that is our P value, the initial principal. 8% is our rate, we're going to rate it as 0.08, and then T is 1 year. So we're going to type in our home screen 1,000, and then E is a number on your calculator, caret, 0.08 times 1. So I'll grab my calculator. Just go to your home screen. Get out of there. Okay, 1,000. Now I'm going to use the E button that's right here above the natural log button. So I'm going to say second and the natural log. And then 0.08 times 1, which is just 0.08. And I get 1,083 and 29 cents. Okay, same thing here for number 19. You're going to type in 800 and then E caret, make sure it's 0.07 times 3 on your calculator. And I'm not going to skip ahead to the next one. How long will it take for the account balance to triple if you're going to collect 5% continuously? Now again, they didn't tell you how much money you invest, and I don't think it matters, because if it's going to triple, it'll always be in a 3-to-1 ratio. So I'm going to write it like this. Now this time I am going to have to use some technology for sure. And again, I'm going to use my calculator's table function. I'm going to type in, you don't even have to type the 1, we can just type E to the 0.05. And then instead of T, I'm using an X. And then I'm going to go to my table and find out where it comes out to a triple value, which would be 3. So trace, trace, trace. Oh, there it is. Roughly 22 years. And again, it's an approximation, so we're just going to say about 22 years. And then, what do we have at the end here? Fish and Wildlife Service. We have an endangered species list. And the number of endangered species can be modeled by this equation. And be careful here. When they make models, they have to set like a time where they're going to pretend time actually began. And in this case, it began in 1972. So the original amount of endangered species back in 1972 should be the initial value, which we know is the number in front of the E. So we're going to say about 119.6 is kind of weird, so let's say 120. Graph the model and use the graph to estimate when the number of endangered species will reach 1,000. So grab your calculator, go to y equals, and we're going to type this in. So 119.6 E, and then 0.0917, and then again, instead of T, we got to use an X. Now, our window, remember, was set up for the last problem. I'm going to keep it as 0 to 10 just for now. I don't really know, well, actually, I kind of remember this problem. Let's change it to say 0 to, oh, geez, 0 to 30. And I still might be wrong. I don't quite remember what we have to go out to. But I know my y's are supposed to figure out where they reach 1,000, so I'm going to go a little below it and a little above it. So how about 900 and then to 1,100. And since I'm only going up a couple hundred, we can probably count by 20s or 10s and be fine. The scale doesn't really matter, it's just going to take you longer to scroll. So if I can see the curve, I'm good. Oh good, I can see it. Alright, let's hit the trace button, and then let's keep going until we can get the y value as close as possible to 1,000. That's pretty close. So somewhere between here and here, so about 23. So we're going to say that t or x equals 23, but that's not what they really want to know. They want to know what is the, when will the number of endangered species reach 1,000? Well, if t is 23, that means 23 years later. And remember, time started in 1972. So, let's see, 1995 is what I was going for. 1995. And again, it's just an estimation. A lot of things could have happened in the history to make that a little different, but we're estimating here. All right, that concludes our lesson. That was a big long one, sorry.